from our last lecture, we came up with this example where from the top view, we saw a part of the circle, and as we were setting up the equations or the integral that we're going to integrate, we came up with something like this, which is not impossible to do. In fact, it's probably not even that hard. But the idea of circles is going to come up for us quite a bit, and so I think it might just be good to be prepared to handle circles in an easier manner instead of always having to come up with this 1 minus x squared or 1 minus y squared business. And so what we're going to do is we're going to take a look at problems like this and allow ourselves to go into polar coordinates. Okay? And polar coordinate for us will make things a lot simpler, I think. So if you remember the relationship between Cartesian coordinates and polar coordinates, I don't have my set up yet. If you remember the relationship between them, there was something with an r cosine theta and r sine theta business. Does that sound familiar? There's something with an x squared plus y squared is equal to 1. And so if x is whatever x is, oh, so let's start off by looking at the equation, and then let's try to justify what happens to the rest of this stuff. There's actually a third equation with a tangent or something like that, but we're not going to worry too much about that. Let's just focus on the x and the y business. And what happens is that in Cartesian coordinates, we're looking at a piece of a circle or something that can be described easily with polar coordinates. And what we want to do is we want to transform that back into r's and thetas. Now, for us to read r's and thetas, let's give this a radius. I think the radius was just 1 in our example. For us to look at r's and thetas, we're looking at like the radial distance. You know, the polar coordinate graph paper that we have. And so what we want to do is we want to try, if we want to go back to r's and thetas, we want to be able to express one of these sectors. Instead of your usual rectangle delta x, delta y business, we want to look at it now with r's and thetas and how things are going to change. And so we're going to go past this and take a look at one of these sectors instead. So if we take a look at that sector, we have to try to see how we can replace the area element of the delta x delta y into the area element with a d delta r delta theta. You remember the volume of or the area of sectors? I forgot. Theta over times r squared. So it's 2 pi r. Area, yeah, just an area. So pi r squared. So what? Should it be just the theta over r squared times 1/2 theta? Okay. So how is this related to this? Um, well, if we're taking little cuts and we're making our cuts according to the polar coordinate measurements now, we're making angular cuts and angular distances with theta. So this will have, like, if we can measure this angle, this is how our theta is going to be changing, right? So I think our angle here is going to be an angle of delta theta. And then our r, well, this is really just a portion of the sector, right? It's not quite the whole r business. So it's more like r sub I and r sub I minus 1 kind of thing, right? And so this is more like, what is it more like? To find this area over here, this is going to be more like r sub 1 squared minus, or r sub I squared minus r sub I minus 1 squared. Is it more like that? So that the area here, and I'll call it delta A, is going to be 1/2 theta. Let's put theta first. Delta theta times r1 squared minus r, or ri squared, ri minus 1 squared. Okay. Oh, the thing in parentheses, look at it. What can you say about it? It's a difference of 2 squares, right? So let's, I don't know what else to do, so let's see if we can factor it. What now? Ri minus r sub I minus r sub I minus 1. This is just the difference of the r's, right? So now we have this thing left to worry about. Okay, now what is that? It's maybe not exactly but as your cuts and your partitions get smaller and smaller, the r sub I and r sub I minus 1 are almost going to be equal to each other, right? So we could just say that's like 2r sub I. So in as we get larger and larger, and we're going to take the limit as it goes off to infinity anyway. So we're going to deal with that. So this is going to be about the same. So it's just going to become twice as much. And so it looks like our area element isn't going to be exactly delta r delta theta like it used to be, just the delta x delta y. It actually will have an extra r in it. So that's what happens to our delta A. And as we let the number of partitions go off to infinity, and I'm being kind of loose here, but there's partitions for the theta, and there's partitions for the r that make up this thing. So there's technically two variables that go off to infinity. Then we see this delta A, the area element that used to just be the delta x delta y or dx dy, is now going to become not just delta r delta theta, but an extra r pops up. So that is our big story here in polar coordinates when we're doing our double integrals and changing to polar coordinates. Yeah. It would work, but that's a different story, because now this is what we're doing is an actual transformation from two variables to two variables. So that in itself is something that we technically haven't done. We're going from xy, two variables, to r theta, another two variables. And so when we do that transformation, we're going to be required to do something else. And maybe I'll get to talk about that at the end of class today. So when we're having a problem, when we have a problem with x and y, and then we notice that our region, r or d or whatever it is, has a circle or is a part of a circle or is a whole circle or something to do with circle or something to do with a polar coordinate function or region, and we decide that we want to change it into polar coordinates with hopefully an easier way to integrate, then whenever we do this transformation, you just have to remember your r. Okay. So the first few times you're going to forget, but eventually you'll remember. Okay. So let's again look at this problem that we have over here. I don't know if I should try to do it in here with very, very little room left. So I know from the drawing, and maybe you would need to redraw it, but I know from the drawing that this is a quarter of a circle that we're looking at with radius 1, right? So the region is a quarter of a circle. So when we're doing this double integral over this region, and we want to change it to polar coordinates, what we're going to do is we're going to figure out what the polar coordinate limits are. So the polar coordinate limits, according to this, would be, I need to know how how far my r is going to go. Now, your r is a radial distance from the origin going outward. And so radial distance from the origin going outward, how far am I going to go? What? Just to 1, right? That's the radius of the circle. I'm going to go as far as 1. Start from 0, end up at 1. And next I need to figure out my angle for theta. And so my angle for theta just is going to start from the positive x-axis and however far I'm going to go. So positive x-axis has an angle of 0. And how far do I go in this case? Okay, 90 degrees. So this is our limit. These are our limits for your integral. So now we're going to change our integral to write in polar coordinates. Y, well, I can't integrate y in polar coordinates. So what's y equal to again? R sine theta. So that's y. And then my dA is going to become r. So there's an extra r that pops up here. And then dr, d theta. Now, before I write d theta, I'm going to stop at dr for a second. R limits are from what to what again? 0 to 1. So that was already figured out. And then my theta limits, d theta, go from 0 to pi over 2. So if nothing else, my limits of integrations are constants. That's always good. Okay, versus the limits of integration that were not constant, not only not constant, but one of them has a square root. And again, not impossible, but I think it might be a lot better if you work on it with this. Okay? Does that make sense? That's pretty interesting. It's pretty cool, huh? All right, let's just dive into doing a whole bunch of examples like we did last time. And then after a while, we'll see if we can come up with some other application. Ooh, look at this. Let's do this one. There is a lot of square roots in this one. Are you guys scared? All right, looks like we have a problem to do. You have 5 minutes to solve this? We can do this in 5 minutes. All right, let's see. All right. So the first thing you want to look at when you're given a problem like this, it's an actual double integral, right? And you're seeing some square roots, but what you have to do is look at the square root and say, hey, that that looks like a circle. It doesn't look like a circle to you just yet, but after a few of these, you'll start looking at these um, equations and say, hey, that looks like a circle. So what I'm going to do is I'm going to work backwards, and we're kind of used to having some information and then writing out drawing out the thing, drawing out your region, and then coming up with the limits. But I'm going to go backwards here, and I'm going to notice that my y is the inner integral, and my lower limit for the inner integral is a negative the square root of 4 minus x squared and positive square root of 4 minus x squared. And then my outer limits, x, it looks like goes from negative 2 to 2. So what I want to do is I'm going to attempt to draw this. And to begin thinking about drawing this, because it looks really complicated, what I might want to do is I want to maybe focus on taking a look at this relationship, either the negative or the positive, it doesn't matter. Because if you take a look at that and say y equals the square root of 4 minus x squared, and say, hey, what if we square both sides? I don't know, square both sides. And then what if we, bring the x squared over to the other side? And then you have a circle, a radius 2. And so I'm hoping that you'll see this today and you'll do a few more of these types of problems. And then from here on out, when you see a square root of some number minus something squared, that you're going to see that's a piece of a circle. And what this tells us is that we have the bottom part of the circle, and we have the top part of the circle that make up your f of x functions. And then your x limits tell you where to start and where to end, and conveniently enough, it goes from negative 2, the edge of one circle, and positive 2, the edge of the other circle. And so this region that we're integrating over is just a full circle. And sometimes you might get, the outer limits might go from 0 to 2, in which case, well, it's only half of a circle. Or sometimes your inner integral might go from 0 to the square root of 4 minus x squared, in which case, well, that's the top half of the circle. And then if you go, appropriately enough, then you can figure out how to work that out. So being that your region is a circle, you probably want to go into the polar coordinates. So all you have to do now, if you're going to go into polar coordinates, is describe this region that you have, which happens to be a circle, and describe that in polar coordinates. So what's my circle going to be in polar coordinates? R goes from what to what? 0 to the radius 2, and theta goes from all the way to pi. And that's it. You're almost done. Just have to write the rest of your integral accordingly. Remember that x is r cosine theta and y is r sine theta. Yeah. Yeah, it looks like your theta, if it's a full circle, it's going to go from 0 to 2 pi. And so the way the polar coordinates work seems independent of your radius and your angle. Yeah. Multiple times? No, we don't want to go multiple times. because we're looking at this as a region. We're trying to describe the region, and so we don't want to go past 2 pi. All right, that was 5 minutes. I'm done.
Why did you say that? Why did you choose square root of 4 minus x squared as opposed to negative?
Oh, I could have done that too. And if I did, I would square both sides and it would become positive anyways. It would be the same thing. Yeah. Well, it matters because the negative is in the bottom and the positive's on top. But aside from that, when you're just trying to figure out that it is a circle, then this is the way to show that it's a circle. I don't think so. This is just showing you that this is in fact a circle. That when you see this function over here, these functions are all parts of a circle. And it's up to you to convince yourself that it's the top, the bottom, the right, or left half. Well, it's up to you how you want to set this up. Convention is usually the theta is last, but that's not a hard fast rule. So you can put it in any order you want, just as long as you're consistent with the with the with the boundaries. Yeah. All right. All right. So after doing that, we have our integral, the inside integral. Well, the integrand itself is going to be 2, and then x is r cosine theta minus r sine theta. And then this is where you don't forget the r. And then depending on what you want to integrate first, usually r, but it doesn't matter. It's up to you. And then that's when you do your limits. 0 to 2 for r, d theta goes from 0 to 2 pi. Yes? No, you shouldn't. Your answer should be the same. Okay? So I'm not too interested in doing this integral, but I want to show you another aspect of this integral that we've seen when we first started talking about it. And I may have gone really quickly on, I think it was on Monday when we were talking about it. But the limits for both the inner and outer iterated integrals are all constants. So there's a lot of neat things that we can do when you have limits that are constants. One of them is being able to separate the different variables. So what I'm going to do here is I'm going to notice that r is a common factor, and I'm going to factor that out. And so I would have an integral from 0 to 2 pi, integral from 0 to 2 of r, and then I have 2 cosine theta minus sine theta after the r's are taken out. Oh, there's an extra r here, so let's just square that. Okay. Now, the inner integral is with respect to r. The thing that's in parentheses does not have any r's in it. And again, this only will work if you have constant limits. So I can take this out as if it was a constant, take it out of the inner integral as if it was a constant, right? So I have 0 to 2 pi. The thing that I took out, 2 cosine theta minus sine theta. And then I took that out of this integral, 0 to 2 r squared dr. And then it's still an iterated integral, d theta. And now, if I notice again, the thing that's in the square brackets does not have any thetas in it, right? It's independent of theta. In fact, if I were to do that integral, I'm just going to get a number, which is a constant. So this is constant with respect to theta. And well, you know what we do with constants, take it out. Now I'm dealing with two integrals that I can do separately. I don't have to do that iterated integral business. And isn't this a lot easier? I think it's just going to be 0. Well, no, not because of the limits of integration, because it really depended on what your integrand was. So if I just had a y in there in my integrand, then maybe it wouldn't be 0. It's equal to 0 because this goes from 0 to 2 pi, and the period is 2 pi. So if your period was not 2 pi, then it wouldn't be 0. Not necessarily. In any case, doing integrals separately would be a lot easier than keeping track of an iterated integral from inside out. Okay? In fact, you could do the first one in your head, right? R cubed over 3. Yeah, so 2 in there, and 0 is going to be 0. So that 2 cubed over 3, that's 8 over 3. So, and then, again, the sine and cosine, the 0 to 2 pi will make it become 0 anyway, so the whole thing is going to be 0. As long as the limits are constants, there's a few more stipulations. I think the limits are constants, and make sure that these are all factors. In other words, if you had an r plus theta in there somewhere, then you can't break that up. So, you can't, yeah, discontinuous stuff, but it'd be finitely discontinuous. Don't let it go, man. Just let it go. I know, but don't dwell on it. Is what I'm saying. Okay, is this okay? I'll stop here, and then let's do another problem. I don't know if I want to do this problem. Oh, we don't have any more problems? Let's find some easy problems first. This is easy. All right, let's do this. No, let's not. Let's pick an easy problem. Sorry, I have to go through find my book. So chapter 15, right? We're on chapter 15. This is section 15, 15.3. Oh, 15.3. Which one should we do? 11, 12, 13, 14? 12? Let's start off with 12 and then maybe we'll do 13. All right, so double integral, we have the cosine of square root of x squared plus y squared dA. D is a disk, the center at the origin, and radius 2. So immediately, disk, radius 2, you want to think polar coordinates. So we can draw this. I don't know if it's useful, but the whole idea in drawing, for me at least, is to try to figure out the limits in polar coordinates. So, by the way, just as an exercise, we're not going to do it, but just as an exercise, what if I wanted to, say, integrate this with respect to x first? And so I would draw a line perpendicular or parallel to the x-axis, and I try to figure out which function I'm going to go into and get out of. And then I'll have y limits that are constants. So if you were to do it using Cartesian coordinates, what's your lower limit going to be going into the function? Negative what? So this is a piece of a circle that has an equation x squared plus y squared is equal to 4, right? And if I want to go into my x equals something with a y function, I would solve for x. As I solve for x, I would need to take the square root. And when I take the square root, there's some plus minus business that's happening. So on the negative side must be the negative square root of 4 minus y squared. And the positive square root of 4 minus y squared. Okay, so like I said, whenever you're dealing with circles, these functions are going to pop up a lot. And then your y goes from what to what? 0 to? So if I go from 0, I would be here, and that would be the top half of the circle. But if it's the full circle, we're going to go minus 2 to 2. Oh, if you were doing this in Cartesian coordinates, this is what you would have. And again, we don't want to do it that way. So let's go back to doing this in the polar coordinate way. Back to the question about r's and thetas. What's my r limit going to be? 0 to 2. And my theta limits? It's the whole disk, so it goes from 0 to 2 pi again. Okay. Later on, we'll see more examples where it's not the whole disk. Okay. And so now we're going to change everything back here. Our integral is going to be the cosine of, now I want to change this into r's and thetas. And x is equal to r cosine theta, y is equal to r sine theta. But what's x squared plus y squared? That's r squared. Square root of r squared. Right? So that's just cosine of r. And then the dA becomes r. dr goes from 0 to 2. d theta goes from 0 to 2 pi. That's it. Now we could solve for it as an iterated integral, or do you see any thetas around? No theta, so you can split this up. Wow. Eavesdropping. Siri just went off. Okay. So if you could split that up, and then now you have two easier integrals to work with. I mean, they're just as easy, except they might be complicated because it's iterated. You go inside out. But if you do them separately, I think that might come out a little bit easier. So the first one is just going to be 2 pi. The integral is going to be theta, evaluate from 0 to 2 pi. That's 2 pi. Now the second one, without doing it, can you just tell me what we should do? How'd you solve for this? Flashbacks to Calc 2. They're taking the test right now, probably by parts. So it's an R and a cosine R. So you probably want to do this by parts. Okay. You can go ahead and do it yourself. Let's move on. Questions? Yeah. Yeah, for the cardioid, your limit for R will not be constant anymore. And in that case, you cannot do the split up that we've been doing. So for any other shape that's not a perfect circle, that's not a circle centered origin, you might have to do some other things. So this is only the this only this trick only works if you have constant limits. All right, let's do 13 from the same section. Oh, this one's an arctan of something. All right, we got an interesting R this time, an interesting region. Can you tell me what this region might look like? This looks really interesting. I wanna graph it in Desmos. But tell me if you can see if you can tell me what this region is going to look like. It's 1 less than or equal to x squared plus y squared less than or equal to 4. So whenever you see those inequalities, just take the stuff in the middle and set it equal to one side and set it equal to the other side, and then it'll be a space in between. It's a what? What? Is it what? Yeah. So there's like a couple of circles. Circle of radius 1 and circle of radius 2, right? And then this region starts from the circle of radius 1 and goes out to the circle of radius 2. So the circle of radius 1 is empty. Okay. Y goes from 0 to x. Okay, well, like I said, set them up individually. Y is equal to 0 is, that's just, what's y equals 0? That's the x-axis, right? Y equals x. Do you see it? We could probably assume that this is happening in the first quadrant. So we can say can probably say that your region looks something like this. Oh, wait, I went too far. Like that. So is that clear that R goes from 1 to 2 now? So R doesn't start from the origin. It's a radial distance going outward. And it starts with 1 and ends at 2, not at 0. And theta goes from, and the line y is equal to x, the slope is 1, so you can figure out that the angle is going to be pi over 4. Okay. So now we're ready, almost ready to transform this. We need to figure out what y over x is. What's y again? Oh, look at that. Just tangent theta. Arctan of tangent theta is what? I just went over this with some pre-calculus people. And this is only true, by the way, if your tangent is restricted. Your theta is restricted between minus pi to pi. Which ours is, yeah. It goes from 0 to pi over 4, so we're all good. So that is our integrand. All right, let's set up our integral. We're ready. We have the limits. We have our integrand, which is just going to be theta. So we have a double integral. The integrand is just going to be theta because all that kind of simplified out. And then the dA always has an r. dr d theta. The r limits go from 1 to 2. The theta limits go from 0 to pi over 4. This one I think we can actually do. The first one that's easy enough to do. The r and the theta are just factors that we can split up. So we can split this up to 2 separate integrals. Let's go theta first. And then our r goes from 1 to 2, just r. Okay. So theta squared over 2, pi over 16, pi over 32 times, oh, I don't know, whatever. So this is the easiest set of integrals that we've had. So you can work this out. Any questions? Okay, so that was a cool problem. That was the first interesting one where it didn't go all the way up to 2 pi, and then even our radial distance didn't go from 0 to whatever. It went from one number to a different number. So that was kind of interesting. All right. Questions? Let's try another problem. Oh, I don't think I told you. You can find areas using double integrals. I don't know. I think I was going to tell you that next section. Double integrals have been usually for finding volumes, right? The base is the region, the two-dimensional region, and then it gets kind of projected up on the surface. So the surface is whatever shape it is, and then as it gets projected up on the surface, then it's going to be the space in between. Does that make sense? In fact, I did some of this stuff after class. So you can see that we're actually looking for volumes of these things when we do a double integral. Does that idea make sense? What if your surface is just 1? The plane z is equal to 1. What can you tell me about that volume that you're looking for if your surface is just the plane z is equal to 1? It's just going to be the area times 1, right? I mean, if you're in physics, then you're worried about units, then you'll have a cubic measurement. But it's still equal to the square area numerically. Okay, so I'll probably make that clear next time when we talk about the applications. How about find the volume of a given solid under the paraboloid and above the disk. Should we do that? Below the cone and above the ring. All right, let's do number 20. That looks cool. Okay, so I don't know if you guys know it, but this is a cone. Z is equal to the square root of x squared plus y squared. If you square both sides, you get z squared is equal to x squared plus y squared, and that's almost like a hyperboloid. It's that cusp between the hyperboloid of one sheet and two sheets. It's like right before hyperboloid of one sheet becomes a hyperboloid of two sheets, there's a split second there when it becomes a cone. Anyways, so you have a cone, and in the bottom you have a ring, kind of like that same ring that we've had. And you want to find the volume of that space. I probably butchered this picture. Don't worry, I'm going to do it on the CalcPlot 3D, so it'll look a lot nicer. I think I'm going to do it there. Anyways, the point is that this is going to be your f of x, y, z, or f of x, y, which is what z is equal to. That's going to be inside of your integrand. It's going to go inside of your integral. And your r is going to be that two-dimensional ring again. It's the same ring that we saw earlier, 1 and 2, except this time we're going to go all the way around. Okay? So our r and theta are what? R goes from 1 to 2 again. Theta goes from all the way around 2 pi. And we have an x squared plus y squared under a square root. What is that? This is r squared with a square root, so that's just going to be r. So that r comes from the square root of x squared plus y squared, but then we have another r that comes from the dAs, don't forget that, so that's going to be an r squared inside. Limits go from 1 to 2 for r, and theta limits go from 0 to 2 pi. Okay. So what do we have? We have an integral that has no thetas in it. Let's move all the theta out. And then let's just focus on integrating r squared from 1 to 2. Now I can do this in my head. 2 pi for the first one, and the second one is 8 minus 1, 7 over 3. Is that right? Yay. Yeah, 14 pi over 3. See? Simple enough, you could do it in your head. Maybe not. You just work it out anyways. Theta 0 2 pi r cubed over 3 1 to 2. Okay. Good. Let's see. Let's try some more. This problem here, the one that I have, it's one of my favorite Calc 2 problem, volume of revolution. So this actually can be done with a volume of revolution. You start off with a circle and you take off some parts of it. And the hardest part, I think, of that is the limit. Well, putting into polar coordinates makes things really easy. And that is really similar to oh, I thought I saw it. Inside the sphere and outside the cylinder. Yeah, it's similar to this. Number 22. Oh, I wanted to draw a picture of this. You guys want to see it? Yeah, okay. Well, let me get back to this problem. Oh, I have to check if this thing does polar coordinates. Ah, it doesn't. It does. Polar coordinates. Yay. 1 to 2. 0 to 2 pi. And the function, what was the function? Square, or the cone. Square root of x squared plus y squared. Oh, let's take that other function out. There it goes. Pretty cool, huh? It's like the stadium. What's that called? Rome? Coliseum. It's like a coliseum. Interesting. So this is the picture that I attempted to draw. It's pretty close, huh? Should I put it right next to it? Pretty close. No. All right, it's not close. Whatever. Okay, let's do another example. This one inside a sphere and outside of the cylinder. So we have a sphere, radius, what's this? Radius 4, sphere radius 4, and we're drilling a hole. The cylinder, we're taking out a cylinder, and so that has radius 2. So here's your sphere. There's a hole that's been dug out. Oh, it's already time. Anyways, if what you want to do is you want to look at the shadow on the XY plane, and the shadow on the XY plane is going to be another circle. And then so the other thing to do is to solve for z, because remember you want z is equal to f of xy. But when you solve for z, you'll get a plus or minus. That represents the top half of the hemisphere and the bottom. And so you could just do the top half and double it, multiply by 2. Okay? So that's enough to get you thinking about it. You should try to do it. If not, don't worry about it. It'll probably be on the test. All right. See you guys tomorrow? No. Oh, Monday. Sure. Piece of cake.